Hello, everybody. Today we are taking a look at lesson 7, which is a titration analysis. So basically, we're going to be relating solution chemistry to the lab. Before we get started, let's refresh solution chemistry. It takes 50 milliliters of 0.35 mole per liter sodium hydroxide solution to completely neutralize 155 milliliters of sulfuric acid. What is the concentration of sulfuric acid? Right. So whenever you're doing one of these reactions, you first need to write a balanced reaction. So we have sulfuric acid reacting with sodium chloride. This is a neutralization reaction, which is the same as a double replacement reaction. What's going to switch places are the Na, the sodium, and the hydrogen, because they're both positively charged. So the cations are going to switch places with each other. This is then going to form water and sodium sulfate. Okay, from here, you're going to balance this reaction. I believe it's 2 and 2. Yep. So now let's list our known and unknown. We have 50 milliliters of NaOH with a 0.35 mole per liter concentrate. I usually like to write moles per liter when I am doing Stoich. And then to the solution completely neutralizes 155 milliliters of sulfuric acid. What is the concentration of sulfuric acid? Great, we have a bunch of information here. From here, we're going to take our known, which is this, to find our unknown. Start off with 50 milliliters. Again, if you don't like the milliliters, you can convert it into liters. I am going to work with milliliters just because it's less conversions. Multiplied by our concentration. Okay, liters cancels out with liters. Now I have millimoles. As long as the base unit is moles, we can use our mole ratio. You divide by 2 moles of NaOH and multiply by 1 mole of sulfuric acid. I forgot to write NaOH here. Okay, so what's canceling out? NaOH, NaOH, mole, and mole. You have moles of unknown. We are looking for concentration. There is 155 milliliters of this. So I'm going to divide by 1 over 50 milliliters of solution. Milli cancels out with milli, and you're left with moles per liter of sulfuric acid. Once you calculate that out and round it to the appropriate significant digits, you get 5.6 times 10 to the negative 2 moles per liter of H2SO4. Okay, let's get into titrations. So when you are doing a titration, it's a very specific setup in the lab. A titration is used to determine the concentration, so it's always going to be an unknown concentration of a sample. Okay, we'll talk about where the sample is placed in a titration. A sample is placed in the flask with a known volume. So the thing about a sample is we don't know its concentration, but we do know its volume. The burette, that is not how you spell burette, that's how you spell burette, is filled with titrant, which has a known concentration. A solution of highly certain concentration is called a standardized solution. So remember in the solutions unit, we were making standard solutions. It were solutions where we knew the concentration was going to be 0.12 moles per liter. A sample is a chemical that can be obtained of high purity and the mass can be measured at certain T. Okay, so we're going to do some sketching here. So first of all, we have a stand that holds the burette. My artistic skills. Okay, and in the stand we hold the burette. The burette kind of looks like this. It has like a little bit of a point at the end, and then it has the valve on the side. And then underneath the burette, we have a Erlenmeyer flask. Okay. In the flask, you place the sample. Okay, so the sample starts in the flask in the beginning. Then in the burette, you will have your titrant. Okay, so this has a known concentration. Okay, and in the flask, you have a known volume. Okay, so flask starts with sample. Okay, known volume. Known concentration. Titration curves are used to determine when a sample is completely neutralized. This is represented by an equivalence point. Or for short, EQP. To find the equivalence point, find the middle of the inflection point. What is an inflection point? So if we're looking at this diagram here, you'll notice that the inflection point is here when it jumps from in pH. You find the middle of that and it'll give you the equivalence point. So the equivalence point for this graph or this curve is going to be a pH of 7. Okay. So I'm going to give you a little bit of an anatomy of this curve. First of all, here, if we were just generalizing this graph, this would relate to the volume in the flask. okay? This, on this side, the responding variable would refer to the pH in the flask. Okay? Now, before we move forward, I'm going to give you a general idea of what a strong acid and a strong base will be. A strong acid, the pH is going to be between 0 and 3, and a strong base, the pH is going to be between 11, 10-ish to 14. Taking that information forward, it's going to help us read some of the curves. So we're going to start off with the first one, equivalence point of 7. So let's draw that. You're going to start off with your curve, volume, pH, and then we're going to first start off with, there's two scenarios here. The first one is a weak acid is titrated with a strong base. Okay, so there's our 7. Weak acid means it'll have a pretty high pH, so I'll go there. And strong, it's going to be very high. Okay, so let's label that. That's my weak acid and my strong base. Okay, and then there is my inflection point. It's very roughly drawn, guys. It's very hard to do on this thing. The next situation we can have is a strong acid with a weak base. Okay, and the inflection point should be give or take the same. Sorry, the equivalence point. Okay, so the second scenario here is a strong base. Oh, and you can also have strong base and strong acid. And it can also be flipped around. Oh, sorry, I've made a mistake here. That should not be strong. That should be with a weak base. Give me a moment, I'm going to return with the right curve. All right, sorry about that. So there is my curves. This one is a weak acid with a weak base. This one is a strong base with a strong acid. You will notice that both of them have an equivalency point of around 7. Let's move on to the next one. If you have an equivalence point greater than 7, so what most likely is happening is there's your 7, is you are having a weak acid titrated with a strong base. Okay, and here we're going to have our volume of titrant, volume of titrant. Okay, so now this is when the equivalency point is greater than 7. So we're going to start off with a weak acid, and then it's going to pull the curve up to a strong base, and then you're going to notice that your equivalence point is greater than 7. Okay, One thing that I forgot to do down here is what are some good indicators? So when you're looking at a good indicator, you want to have your equivalency point be in the range. So if we were looking at the strong acid, strong base with the equivalency point of 7, a good indicator for this would be bromothymol blue. The reason being is because 7 is part of that range and it's not very drastically apart. So you always want to pick something that's within the range. For this one, we're going to have a equivalency point that's greater than 7. So you want to pick something above 7. A great indicator for this would be phenolphthalein. And this is actually used in titrations a lot. Okay, let's go to the last scenario where we have a pH that's less than 7. This is when a weak base is titrated with a strong acid. It's going to have a pH of less than 7. So when drawing the curve, we're going to have our pH and the volume of titrant. Sorry, I believe I said volume and flask in the black slide. It should be volume of titrant. I'm just going to correct that. Yes, you do start with that right here. Volume of titrant. Okay. So now we're starting off with a weak base. So we're going to be, so here's my 7. Ooh, here is my 7. You're starting off with a weak base. You're starting off up here. And then you draw the curve. So now we have a weak base titrating with a strong acid. And that's going to pull my equivalency point below 7. So a good indicator for this would be maybe, oh, what is happening? Orange 5, something in that acidic range. Depending on, if you have more information, then you would pick a very specific indicator. All right, here we have a curve. And from this titration curve, we're going to look at some things. So the first thing it says, looking at the curve below or above, identify the following. A, label pH, volume of titrant on curve. So we know that the volume of titrant goes on the bottom there, and then pH is our responding variable. So this is our manipulated, that's how much we're putting out of the burette, and then this is our responding. What is the pH of the sample? So remember, sample in the flask, currently before anything is measured, the pH is going to be the starting point of the curve. So I see here that my sample, has a pH of about 3. What is the pH of the titrant? So the pH of the titrant, once we've gone past our inflection point, our pH of our titrant is going to be on the other end of the inflection point. So if I were to read across here, I would say it's about 12, 12.5. Label the equivalency point. So the equivalency point is going to be right here in the middle of your inflection point. So find that there, and I label it my equivalency point. Okay, and then lastly, what is the pH of the equivalency point? So I'm going to read across. I think it's about approximately 8.5, almost 9. And when you're doing this, obviously it will be much more precise. Yeah, I'm going to go with about 8.5. What would be a good indicator to show the endpoint? I would have to go with phenolphthalein. And we are not going to answer the last question. Actually, we can go for it. So what is the nature of the sample and the titrant? So the sample is a weak acid. It's above 3. So we're going to say sample is acidic and titrant had a pH above 7. So we're going to say that it is basic. Okay, so let's look at titration data. When collecting data from a titration, we will add titrant into the flask with the sample until we reach the equivalence point. Or in our case, we'll be able to see it with a color change. The goal of a titration is to determine the concentration of the sample. You perform a titration of, so let's do an example. For example, you do a titration of 25 milliliters of NaOH with 0.325 HCl. You end up with data table like this. Okay. The first thing you're going to do before we go into it, I want to identify what is your sample. So remember, your sample is your known volume. So NaOH is my sample because it has a unknown, I'm going to give you the facts as to why. A, it has an unknown concentration, but most importantly, it has a known volume. We control how much sample we put in. Oh, not known sample, known volume. What is your titrant? The titrant is our known concentration and unknown volume. So my titrant is HCl because known concentration. Okay, so here we have our data table. You're going to notice the data table is set up pretty, they're usually standardly set. These two columns may interchange, but just know that you are always, make sure you know which one is your initial and final. So step 1, what you're going to do is determine the volume added. When determining the volume added, you must subtract initial wow, that's a big line. You must subtract initial volume from final volume, also known as final minus initial, which is a very common way of doing science. You almost all the time you are taking final minus initial. Okay, so looking at our data table, we are going to subtract these numbers. So 16.5 minus 0.16, that's 15.9. This is 15.3. So always bigger number minus the smaller number, if that also helps you. 15.2. You can't really have a negative volume. The next step, eliminate any trials that are not plus or minus 0.2 from each other. So you're going to go back and you want to look at numbers that are close to each other. You want to see if there's any bad trials that you had. Most likely when you do a titration in the lab, your first trials are not going to be as good as your last ones. So we're looking at these three numbers here. Okay, they're plus 0.1 from each other. So what I mean by that is if we're on a number line, and I put these on here, I have 15.2, 15.3, and then 15.9. Between these two numbers, it's plus minus 0.1, which is fine. We can go up to 0.2. However, from here to here, it's plus minus 0.6. That's too much. Also, from here to here, that's plus minus 0.7. So this number is not a good trial. It's very far away from the rest of our data. So we eliminate it. That's a bad trial. So trial 1 is eliminated. Average the remaining volumes. So we're left with 15.3, 15.2, and 15.2. So I take the average. So I'm going to say volume of titrant is equal to, so to take an average, you add all the information up. So I'm going to go 15.3 milliliters plus 15.2 milliliters plus 15. Oh, that is not how you write 15. 15.2, 15.2. You add those all up, and then you divide by how many numbers you had, which was 3. The average volume is then equal to 15.23 milliliters, which is the average volume of our titrant added. Step 4 is set up a Stoic statement to determine the unknown concentration of the sample. So you need to write a balanced reaction. You have, what do we have? We have NaOH and HCl. So NaOH plus HCl. This is a double replacement reaction where the cations switch places with each other to produce water and NaCl. Okay, let's do some labeling. We knew the known volume of our of our base, which was 25 milliliters. 25 milliliters. And we knew the concentration of our acid, which was 0.325 moles per liter. Okay, let's go ahead and identify again our sample and our titration. So this is my sample because I know the volume. This is my titrant because I know the concentration. It's asking us to find the concentration of the sample. So we're looking for moles per liter of this. But do we have a volume of our titrant? Yes, our volume of our titrant is actually this averaged volume here. So I'm going to go ahead and carry that averaged volume down. And it is going to be 15. What is happening with this? 15.23 liters. Okay, from there, you are going to then do the Stoich. Okay, I'm going to write the Stoich out and then I'll be back. Okay, so once you set up your Stoich, you are going to start off with your volume of HCl. You can have it in liters or milliliters. If you choose to convert to liters, you must choose to convert the other volume into liters as well. Then you multiply by your concentration, use your mole ratio, divide by volume, and you end up with a concentration of 0.18 moles per liter. The hardest part about titration is setting up your information and using your data. Okay, so let's do one more example together. First things first, you're going to figure out the volume added. So I'm going to go ahead and do all of the subtractions, always final minus initial. So this one is going to be 17.6, 17.5, 17.7, and lastly, 18. Then you're going to ask yourself, is there any trials that need to be eliminated? Well, this 18 trial is so far away from the rest of them. It's beyond 0. plus minus 2, so I'm going to eliminate it. Then you're going to take your V average. Your V average, remember, is the same thing as to your volume of titrant. You do that by adding the numbers together. And sometimes you may only have 2 numbers. Sometimes you might be able to use all 4 of your numbers. It's all based on your data. In this case, we ended up with 3. So my average volume then becomes 17.6. Lovely. From there, we are going to set up a balanced reaction. We have sulfuric acid, which has 12 milliliters. We'll get to putting all the information after. Reacting with lithium hydroxide, which then will produce water plus lithium sulfate. Okay, let's list some information. I have 12 milliliters of H2SO4, and I have known concentration of 7.5 moles per liter of lithium hydroxide. So now, if I were to ask which one was my sample and titrant, this is my sample, this is my titrant. I can also add that my volume of titrant is 17.6 milliliters. Okay, and we are asked to determine the concentration of sulfuric acid. Lovely. So now from here, we're going to set up our Stoich. We start off with our volume, 17.6 milliliters of lithium hydroxide. I then use my molar concentration to convert this into moles. I always forget to balance. This is going to be, I believe, 2 and 2. Okay, so I divide by 2 moles of lithium hydroxide and multiply by 1 mole of hydrogen sulfate. Okay, so it cancels out as moles and moles, lithium and lithium. And then lastly, we need to convert this into concentration. So I divide by 12 milliliters. Milli cancels out with milli, I'm left with moles per liter of sulfuric acid, which is exactly what I'm looking for. I plug that into my calculator, I get 0.55 moles per liter of sulfuric acid. All right, we have one here for you to try on your own. You can unpause and then check your answers. Okay, let's quickly walk through this one. So you're going to first go ahead and get your volume added by subtracting final minus initial. From there, you're going to examine, is there any trial that is kind of not matching or staying within that plus or minus 0.2 rule? And I would have to say it's trial 3. So we've eliminated trial 3. From there, you are then going to average the remaining volumes and you'll get a averaged volume or the volume of your titrant as 9.59. From there, you will perform your Stoich and you should get a concentration of 0.133 mole per liter. One thing I do want you to note, the sample can be acidic sometimes, the sample can be basic sometimes. Sometimes the titrant can be acidic, sometimes the titrant can be basic. A lot of students kind of just put it into their head that the sample is always acidic and the titrant is always basic. That is not the case. It is all dependent on what we are looking for, what the concentration is. So please be mindful and do not ever label it as acid and base.